Be good. Yeah, I think I'll upload the recording to YouTube.
Yeah, I can share from there.
But yeah, I'd say whenever you guys are ready to let her rip.
You want to talk about yeah access to your
Yeah, I guess it depends if he's the only member in the audience, but I'll show in any case. Okay, so I'm gonna share my screen and I'm going to try and show you how you can use RStudio without installing it if you have taken a computer science course before and if you have an account on a certain server. Okay, I have a lot of windows open. Desktop one, okay, good. Okay, so yeah, if you are again a computer science student, if you have taken 141, 145, you should technically have an account on Tux. And if you have an account on Tux, you should also have an account on other servers which are available for students. So if you go to scorpio.usask.ca, it will allow you to access Jupyter Notebooks or Jupyter Lab and RStudio on the fly. You don't need to do any installation. This is like a free RStudio server hosted by the ComSci department. So just click on go to RStudio and it will ask for your username password. This is same as your pause password. So just log in and it should open up an instance of RStudio right within your browser without any extra setup. So yeah, this is just the default RStudio template. You can get rid of most of it, but just to sort of show you around, by default, this will log you in the home directory of Tux World. And if you are just a first year ComSci student, you may not know what Tux is. It's just a server hosted by the ComSci department, which is active 365 days, 24 hours a day. So people just use it to do their assignments and stuff. So by default, if you look on the right side, this is my home directory. That is a lot of core dumps. But yeah, this is just my home directory on the Tux, which is the ComSci server. And yeah, you can go or open a specific file by either upload a file which you have local, or you can just create a new folder here and just some basic stuff. For today's workshop or bootcamp, I think we are going to work with R Markdown.
I have just like a PDF that I'm going to show. So.
Yeah. So my part of presentation will be using R Markdown. So in order to create a new R Markdown file, just go to File, New File, and then you have options for R Script, R Notebook, R Markdown, and a bunch of other options. So R Markdown is just like a combination of a Markdown file and sort of a particular proprietary format where you can use R code inside the Markdown and you can run chunks of code if you wanted to. So hit OK, and yeah. This is just again the default template for R Markdown. And yeah, I just wanted to show you how you can follow along for today's bootcamp if you wanted to. So this will require no installation on your local machine. So this will probably be the fastest way to follow along in the bootcamp. If you're watching it, if you're watching a recording of this, I think you should be able to follow it as well. So if you're not a computer science student, then unfortunately you'll have to install R on your local machine and RStudio, which is an IDE. Again, for ComSci 141 students, this is like PyCharm for Python and then RStudio for R. That's the best analogy I could think of. But yeah, there are other things that I can show you in RStudio, but maybe we can do it at the end, depending on how much time we have left. And yeah, for now, I will pass it along to Matt.
Awesome. Thanks, Guillaume. Just gonna figure out how to share my screen here. So Yeah, maybe I want to do entire screen.
Yeah, I usually do entire screen. Just
Yeah, that's easier.
if something terrible pops up, so be it.
Yeah.
I have 15 windows open. I can't do that.
So you guys can see this PDF I have. Hey, so I guess before I go through the PDF, the PDF it's a R Markdown PDF, as Guillaume was talking about before, and it has chunks of code, and then it has their output. So if you don't know though, like these chunks of code, for example, this line right here, you can make any R script and use the code. So if I just want to do like a simple R script, this would be like where you would enter the code up here, and you can run it, or you could even enter it in the console. But just for this presentation, I'm just going to go through the PDF. So the first thing I want to talk about, I'm just going to talk about some basics. Like Guillaume kind of mentioned, RStudio is like super awesome for a lot of stuff. It handles plots really well. It has a great environment tab to keep track of variables. So just to start off, I kind of just want to talk about like assigning variables. So RStudio, you can use an arrow. So if you want to say X is 45, you would assign it like this. And running the first code it assigns it, then running this part, just X itself will output the 45. Another way you can do that is you can use an equal sign. And if you want to output it and assign it in the same line of code, you would do it like this. So just running this line of code right here would output 27, and that would be the value of Y. So just like any other languages, you can do operations. You have like addition, subtraction, whatever. So here, just for this example, we have X, Y, Z, and we have assigned variables or numbers to each of the variables. And, we can just add them like we have here. And when we don't assign it to anything, it'll output. But if we were to assign this to a variable, it wouldn't output it, like as we saw before. So yeah, these are just examples of operations, multiplication, raising X to the power of Z, division, all just works pretty simply. So yeah, I guess that's like pretty basic for variables, and there's not really much more to say. If, like I said, the signs are pretty basic. There's just division, multiplication, whatever. Yeah, I can't think of anything else. I guess how you would need to do with just individual numbers. But if we want to get into vectors, we use the C. So we would go C bracket and then include everything on the vector. And this is how you tell R that you want it to be like a vector. So this is how you would assign a vector, and then we print it out, and then we have our vector. So then, just like any other language, there's ways to access elements in the vector. So for example, we index it to the third spot, we return the number 3, or we can index it for like a range of numbers. So we want to go to the second to the fourth, so we get numbers 2 through 4. And we can also kind of do the opposite of that by making a vector without stuff. So if we want the vector, but we don't want the third and fourth element in there, we can use a negative sign to take it out. And again, we also use the vector syntax here to tell R that we're removing this vector of numbers from this vector. Here's a couple other examples of stuff we're doing. So like you can make a new vector using the old vector. So you just kind of do what we did before, but you can just assign it to variable like we do here, and then we output it. And then, so here's something kind of cool that I like to do sometimes. If you know that like the 6th position you're going to want to be 4 and you assign it, you can see that it extends the vector all the way to have 6 positions, but it makes these NAs, which can be useful in some situations. And then also on top of numbers, we can add like strings, for example. So if you're keeping track of colors, for example, we can assign that to the 4th position that gets rid of one of the NAs. And for those of you who don't know, NA is just a value that we don't know. And then you can do stuff like this to get like the last item, for example. Like most languages, there's going to be just basic functions like length that you can use. And yeah, in R, it's very much just if you want length of a vector, it's just length bracket, the name of the vector bracket. And when you index a vector using this, it just gives you the last item in that vector. So like we have some operations that we can do too. For example, scaling is very easy. We just multiply a vector with a number, it'll just scale a vector. And similar to like adding, we have 2 vectors, we can add them, it'll just add each element. multiplying, same thing, division, same thing. And a lot of these vector operations can extend to matrix operations. So first we'll go over how to build a matrix. One of my favorite ways to build a matrix is to just create individual column vectors and combine them with the matrix function. And then you tell R, we want this group of vectors and we want this many columns. We assign it to our matrix here and let's output it. And this is what it shows. So you can see that the column vectors are 1, 2, 3, just like we assigned before. Another way you can do it is instead of creating individual vectors that you add together, you can just make an entire vector and you just specify the number of rows and columns and it'll kind of force it into the matrix square shape. So like 1, 1, 2, 2, it'll kind of do the same thing, but we just have one long vector now. And just like vectors, we have simple operations. We can scale, we can add matrices, can multiply matrices, but just to note, R has different syntax for matrix multiplication. For example, this doesn't really work. This kind of just does element pairs. So if it's like top left multiplied by top left, which isn't how matrix multiplication works. You want to use percent sign multiplication, percent sign, and that does the proper matrix multiplication. This is something that when I was first learning R, I think I had like an assignment and it took me like an hour to figure out why isn't the multiplication working. And I just was using not the right syntax. So, and then we also have like functions to transpose a matrix, which is just T bracket, the name of the matrix. We can do inverse, we can which is the solve function. And, you have to make sure that your matrix is not singular. I think the term is right. Otherwise, it'll throw you an error and it won't work because you can't find the inverse of a non-singular matrix. But yeah, no, so like I said, just solve and the matrix name. And I think I messed up my code here because I'm outputting the wrong matrix. Oh no, I'm outputting the right matrix, sorry. Yeah, okay. Okay, so yeah, that's kind of it for like operations and stuff like that. I kind of just wanted to touch on a little bit of like dealing with actual data. So most of the time when you're using R, you're going to be using data and you're going to be using data that either you collected or someone else collected or the professor just gives you. So real quick, how to open a CSV file. If you have an Excel file, you can save file as, and then select CSV. And R really likes using CSV files. It's just a lot easier, the comma delimited files. So this is kind of like the bad way you can do a CSV. You type out the entire pathway where the CSV is saved. So for example, this is where I downloaded the CSV online, SLR07, and I saved it into this R tutorial folder on my desktop. So I have to copy the whole thing. And on Windows, when you copy it, you have to reverse the brackets, which is kind of funny. But anyways, this would work. This does work, and it saves the CSV as my data. So that becomes a data frame called my data. The way I really like is I like using the here function. So same thing with other languages. Sometimes people will create functions and they'll upload them in a package. So anytime you want to use a different package, you need to install it first. So you would do that in like a console. And the function for that is just the word install.packages bracket, and then you would do quotation mark here, quotation mark. I should have included that here, but I guess I already had installed, so I didn't think to do that. But anyways, yeah, so you install a package and then you can just use it. But whenever you use it, you have to specify that you're using it. So that's why I have library here. So when I run this line, it tells me where here starts. So it kind of, this is where I have my project, my R project saved to. So here it just starts there. And then I can go my data, read CSV, and then I use the here function to find the long string here. And this is really convenient because one, I don't need to figure out this long string and copy and paste it and switch around the way all the slashes go. But also because if I send this R script to a friend to look at or a classmate, they're not going to be able to run it on the computer as is with this code. But if I give them the data and they save it in their project file and they run it, it'll work with the here function doing the work for them. So anyways, once we have our data loaded, most of the time you're going to want to try to make some inference, fit some kind of model to it. But before we do that, we're just going to take a look at it. So I use the head function, Headmate Data. It spits out the first 6 rows of the data, just to kind of tell you what it looks like. So the data that I have here, it's got online, it's a pair of data, and it talks about the size in millimeters, the width of a kangaroo's nasal passage versus like length of it or something like that. So yeah, I think these are both in like millimeters, and we're just trying to see kind of how the data is. So the head shows you like the first few columns, gives you rows and columns, gives you a good idea of it. And then this str function, this tells you a bit more. It tells you that they're both integers, right? Sometimes if you're dealing with data that has like male, female, yes, no type things, those will be strings, and you'll have to treat those differently. But this also tells us the amount of observations and the amount of variables. Another way we can find that though is, like most things, we can find dimensions of a vector or a data frame. So number of columns, it'll say 2, number of rows, 45, but that's also what str told us here. We have like summary and table functions. So summary of my data X. So this is giving us a summary of the X column, and this would be how you would index it if you know the name. So my data $.x is how we find this specific column. And when we take the summary of it, it tells us some information like the minimum, medium, the mean, and the max value, and some other stuff. Similarly, we have a table function. This isn't really good for continuous variables, but if we did have something that was like male, female, yes, no, it would give us like, maybe there'd be like half-ish male, half-ish female. In this case, it doesn't really work, right? Because it's a continuous variable, but and then I just do the same thing for y here just to see that. Also, when we want to fit a model, we like to check normality. This is just a better way to get insight into the data and kind of know what to expect when we fit a model. So a great way to do this is to fit a histogram. And that's really easy in R. It's literally just hist and then your column as we indexed before. This line of code, it just sticks the two graphs beside each other versus having one on top of the other, just so it looks a little bit cleaner. But most of the stuff is you can just find like how to put figures beside each other. If you're ever writing up a report and you want to make it look nice, you should just be able to Google the code that you need. Anyway, so yeah, these are my histogram plots, and it's not completely normal. They don't make like a perfect bell curve, but it looks good enough to fit a regression model too. So for those of you who don't know what simple linear regression is, it's kind of just fitting a linear line to a model and seeing if we can kind of get a good fit for this model with a line. So I have a visual for that later. But the way you would fit a model, a linear regression model in R, is with the lm function. So I say lm, we have our variables. We want y to be in first because we're trying to predict y using x. And then we specify the data that we use. And the data was saved to previously as my data. And then I can just output my fit and see what it looks like. We have our x estimate and our intercept estimate. And if I take the summary of this, this will tell me some more information. It'll give me some like the p-values. So we can see that these are both pretty significant estimates. And this also has a bunch of other information here. For example, the R squared will tell us how good the model is fit. So 0.7769 is okay. A really good model will probably be like 0.9. The R squared is always between 0 and 1, and it's kind of like a ratio percentage of how accurate your model is. So this is okay. This is acceptable. And then I'm just going to plot this model. So this is the X and Y, and this is kind of the data. And then the fit that we made is essentially just this line that I have plotted, this red line. And we can kind of see that it's like an okay fit. And yeah, there's some intersections, and it seems like it fits decently. The whole point of this would be like maybe to predict if I have like y is like 800, then I can expect, or x is 800, then I can expect y to be like maybe 260 or something like that. But yeah, this is kind of all I have, just kind of how to create a simple fit. And yeah, so yeah, I guess if Guillaume's ready to share his stuff, this is all I have. So yeah.
Okay.
Yeah. So I actually have a data set that I will be using and showing you how or you can follow along live, or if you're watching this later, you can also follow along. Slow me down, increase the speed of the recording as you see fit. The link should be in the announcement sent by Sean, and then I will also ask him to put that in the chat. But it's essentially tinyurl.com/ms3 R Bootcamp. It will lead you to this Google Drive webpage. You should be able to download both the files. As long as they are in the same directory or same folder, you should be able to follow along what I'm trying to do. And yeah, if you're using the RStudio server, which I showed earlier, you can just click upload and just upload the files that I have provided or I have shared. And yeah, so first things first, this is again RStudio. I guess I'll just show you a little bit around. Let's see. So yeah, I use dark mode, by the way, but apparently it's been said by professors that light mode is good for presentation purpose. So that's why we are going with light mode, but don't use it because you should never use it. You always use dark mode. So yeah, just some basic things around the layout of RStudio is that you have your R console down here, which is where you can run some basic commands and see how it will perform. Your main area of workspace, which is here, you have your code and text. Remember that R Markdown allows you to have text like a Markdown file, but also insert R code with 3 backticks. And then in bracket, you say which programming language this belongs to. So R Markdown has support for Python as well, apparently. But for now, we'll stick to R. And then at the end, you again put 3 backticks, and anything between the 3 backticks will be the R code. On the right-hand side, we have some, you can adjust the size as you need. So here you have some files. If you do some plots, you can get like a very quick overview here or preview. Packages, if you want to install some packages from here, I do not recommend it. Just ignore this for now. Help, if you need help or documentation or any function, this is really good because in the console, all you need to do is type question mark name of the function. So for example, how about mean? So question mark mean will just open up its documentation. And it has links embedded. So if you click here, it will just direct you to the man pages, document pages, whatever you want to call them. If you don't know what the function is called, you can use 2 question marks. And then maybe, let's say I'll just do MEA. I don't know the full name of the function. Then it will list all matches with MEA here. If you know what you're looking for, you should be able to use the search function here. And hopefully you will be able to find what you're looking for. If not, just Google it. But I think this is really good if you know the name of the function. So yeah, on the top, you have some RStudio specific environments. So we will ignore most of this for now because I don't want to go into a lot of technical details. So for most of the presentation, I'll just be hiding this because I don't really need it. So yeah. Okay, so what I'm going to show today, it might feel too much, but what I wanted to show is what you could do if you wanted to use R as like a data processing or pre-processing or data cleaning pipeline. So how you would, or how someone from a more computer science background might use R so that you can have some scalable behavior, and then you can use this for big projects. If you're working somewhere, it is likely that you want to use this with big data sets. So there are a lot of tips and tricks that I've used so far, and I've tried to just accompany them in these code snippets. And yeah, hopefully you can follow along. And if you have any questions, feel free to stop me. If you have any questions while watching the recording, feel free to email me or send me a message on Discord. Okay, so yeah, Wickham. So he is one of the authors of a package called Tidyverse. I think it is the go-to package for any sort of data processing you might want to do in R. So he has 3 rules for being tidy. He says that each variable has its own column, each observation has its own row, and each value has its own cell. If your data set follows this structure, it's good, it's tidy, and it's clean. So that's why he has a famous quote where he says, tidy data sets are all alike. Every messy data set is messy in its own way. And I cannot agree more. Like if you work with real life data set, which is what we will do for this presentation. So this data set is like the COVID-19 test cases and death cases, which was a public data set by the government of Canada. So we'll just try to explore some things, and some of the code snippets were actually used in a pre-processing pipeline for COVID-19 modeling that we did for province 2 years ago. Okay, so first of all, we'll load the library. So as Matt mentioned, you can use it by tapping library, name of the library like this, and it will load it. I'm using a function called suppress messages. I do not recommend using this if you don't know what you're doing. It is kind of a rude thing to say, but don't use it if you don't really know. All it does is just suppresses the messages or warnings that might be printed to the console when you load a certain library. And the reason it prints some warnings while loading the library is because there could be functions which have same names in different libraries. And unfortunately in R, there has not been a good way of making function name unique. So that is why it could print a warning message saying, okay, default mean is replaced by this mean now, and so on. So yeah. For now, we'll be ignoring most warnings while loading the library. But again, don't use this in a real script if you don't exactly know what you're doing. So importing data sets. So as Matt mentioned, CSV is the go-to sort of format for data set, but in Tidyverse, there are a lot of different libraries. So Tidyverse is a collection of libraries. So there is one particular library called ReadR. And ReadR has supports for all sorts of formats. So not just CSV. If you have an Excel file, you don't even need to save it as a CSV. If your Excel file is password protected, you can even open that directly in R. So for that, there's a function called as read Excel. Then you have Haven, which is also a function for SPSS or SAS file. I don't have a lot of expertise in that, but I know there's a function. JSONLite, if your data is in JSON format, and there are a lot more. For this bootcamp, we'll just stick with the CSV file. So readR, the function is known as read_CSV. And the path is just the path of the CSV, which is, this is my local path, but if you just change it to data.csv, it should work. And data.csv again is present in the Google Drive link that I just shared. So. Okay, so we'll try and load the data. I'll be running the code line by line. Hopefully you can follow along again. So there we go. Oops. Okay, so now we have a first warning, and it's a pretty big one. We'll go line by line and see what it says. Before that, when you use R Markdown, you don't really need the console. You can just hit this arrow and it will run the code and it will put the output like right there. And that's like a really good feature if you're doing some small code snippets. For the purpose of the bootcamp, I want to use the console, so I'll be turning it off and forcing it to print to console. So you can just click this setting and you have options for chunk output in line and chunk output in console. So what is a chunk? Essentially anything that comes between these 3 quote or backticks, that's a chunk. So I'm currently forcing it to output it to the console because I have some use case that I would like to show. So we have warnings. It says by default, it used delimiter comma, which is okay. But then it says it made an assumption that the first 4 columns are of type character. So it assumed that they are like strings. And the other columns, it has made an assumption that it's of type double. So when you don't provide a good sort of like the ReadCSP uses a heuristic inside. So what it does is that it will go through the first 1,000 data points and it will just guess. It has like an inbuilt table function where it will start with integer, double, and so and so, and it will find the one which is suitable for most columns. This is good if you have good data set, if your data set is clean. In most cases, again, data set is not clean. And that's why we could provide it with some helpful sort of guidelines to follow so that it will read the CSV in a particular format that you want. In fact, I'll show you what the CSV looks like before we even go in there. So our CSV is data.csv. So let's see. Okay, so this is our data set. It has a lot of columns. Some of them are strings, date, and then numbers. And it might look good from this, but as you can see, some columns are just blank. Some rows are just blank. And if you scroll down, numbers start appearing, which was blank before. And that is definitely not something we should be ignoring. So that is what we will try to fix while going through the bootcamp. Okay, now back to reading the file. So here we did not provide any options. We just said read the CSV, but now we'll give it some options. So by default, it uses the first 1,000 rows to guess. I'll change it so that it uses the first 10,000 rows. Maybe there's something in the last 2,000 or 8,000 rows which was not in the first 1,000 rows. So we'll allow it to go forward. But if your data set is really, really big, this will slow it down considerably. And then we will say to R that anything which is empty, so this indicates the empty. So if there's nothing, treat it as a nan. Nan is just not available or something invalid. Or if it explicitly says n/a, you can also treat it as a nan. So now it knows what to do when it encounters a nan value. We'll run it again, and we again got some errors. And this time it again made an assumption about character and double. So now we will just help it a little bit, that we will go and we'll take a look explicitly column by column and make sure that it reads what we want it to read. So cases and then tests cases, deaths, they're all in integers. They are not doubles. You cannot have decimal cases, decimal deaths. So we want to force it to integer. So you have a lot of data types for columns. I've listed some of them here. You can find more in the documentation. So C is short for character, which is the default that it interpreted for the first 3 columns here. Then we have integer, number, double, logical is true and false, factor, date, time, and so on. If you leave it as question mark, it will again guess based on the first 1,000 or 10,000 values. So now I'm explicitly providing it the column types. And I'm using a function called as paste 0. So we'll go line by line again and see what paste 0 gives. It is essentially just giving me this string. So paste 0 is concatenating 2 strings. First string is n/CCC, and the second string is, because I didn't want to type n 36 times by myself, I just use this function called strrep, and it just prints 36 n's. So I just wanted to concatenate these two together, and one of the functions you can use is paste 0. And yeah, that's how it concatenates. So now I'm saying column types. So here the order matters. So what R will do now is it will go column by column. So this is saying that first column is a number, second column is a character, third column is a character, and so on. And if you don't know a particular what the data type is for a particular column, you can just leave it to question mark. It will again try to guess. Okay, so now if we run this, hopefully we don't see any errors. So yeah, it was successful and we don't see any error here. And I have a comment here where I say that ReadCSP. So this read_CSV is different from what Matt showed, which was read.csv. Read.csv is an inbuilt R function. Read_CSV is the tidyverse function. I recommend you use read_CSV because tidyverse has certain set of nice features that allow you to debug your code way easier than using our read.csv. And it allows you to read a compressed data set. So if your data file is in some weird format like zip or tar file, apparently I was surprised, but if it's tar.gz, it can also read it without compressing it manually. So it has some pretty good features. I suggest you to read some documentation. And again, I would like to clarify that I'm not trying to just teach you functions. I'm just trying to show you what you could do if you know this library. And it comes with practice. If you get stuck, just Google stuff. There is a ton of documentation online. Okay, so next big thing, pipe operator. I believe this is one of the most powerful feature of tidyverse. Most people using R, they don't really come from a computer science background. What this pipe operator allows you to do is write code in a very, very clean way. So the idea is that you take in some input and pass it to a function. So result from a previous operation is invisibly input to the next function's first argument. So if you have some function composition in R, such as H is one of the function, G is second function, which takes the input as output from H, and then you compose it with F, and you want to assign the result to another variable called Y. So this can get messy very easily because in general, function names are long, function arguments are long, and you can have a lot of other things going on. But if you use the pipe operator, you can just rewrite this whole thing like this. So it's like a natural flow of progression kind of thing. So you take X and then you use this pipe operator and then say H. So H is a function and the input to H is X. So this will run, it will get some output, and then that serves as input for G. Then G will perform some operations on that, and then it will again perform as input for F. So it can also be read as and then. So it's like X and then apply H, and then apply G, and then apply F. And I don't think there's an upper limit for how many pipe operations you want to use, but I think if you're using more than 7 or 6, you should probably break it up. Either you're doing something wrong, or you should probably break it up so that it's easy to debug the code. And it only works when a particular library called dplyr is imported, but we just imported tidyverse, it imported everything. So again, tidyverse is a big package that contains a lot of individual libraries. Tidyverse documentation is one of the best documentations I've ever seen with tutorials and codes. Just Google tidyverse and it's really, really good. Okay, so we'll start with a very simple example. It doesn't mean anything, but we'll again go line by line. I'll try to explain what each function does. So SEQ, that stands for sequence. It just generates a sequence of numbers, 0 to 100, nothing special. I'm assigning it to a variable X. So, okay. Oops, X. Now I'm creating just a new variable called polyx. So X is just numbers 0 to 100. I just want to create like a fake example, fake data set to show you how you can use the pipe operator. So poly is a function inside R, which will just start from 0th power until nth power. N in this case is 10. So if you put this, it will return a matrix kind of thing where each column, so the first column is X to the 0, second column or first column is X to the 1, second is X squared, X cubed, X to the 4, and so on. And I'll save the result in polyx. So now if we see what polyx is, it looks something like this. So the first column is just 0 to 100. Second column is squaring 0 to 100. So 1 squared, 2 squared, 3 squared, and so on. Third column is cube, fourth, and so on. Now, let's say you want to perform a row sum. So you want to sum each row. So there's 0, 0, 0. This will all be added together and you will get an output. Similarly, 1 plus 1 plus 1 plus 1, and so on. Then it'll be 1, 0, 2, 4 plus 5 and 2. So we are essentially performing summation along the row. You can perform summation across the column. And then this is, for this example, I'm doing row sums. So there's a function called row sums that literally performs row sums. And then let's say that you want to calculate the mean for some reason. So you say mean. So you get a mean, and let's say you save it in a variable called final result. So you can run this. It's okay code. It's 3 lines of code, but using pipe operator, it could just be a single line, and it's way cleaner, way explicit what you're trying to do. So the first input, in this case, X, was sequence. So another good thing that this offers, it might not matter with small sort of data sets or variables, but you had to save the result of sequence in some temporary variable that you don't really want to use in future. Here, you don't have to do that. So the output from SEQ is input for poly. Poly performs some operations. As we just saw, it creates squares, cubes, to power, and so on. Then serves as an input for a function called asTibble. I'll show what it does later on. And then you serve it as an input for row sums, and finally mean. And you don't need parentheses if you're using functions in pipes. You can have it to be explicit, but you don't need it. So I think this is more like the functional programming paradigm that R supports. So if we run this, it gives you the exact same result. So instead of having this as 3 lines of code, you can just have this. So there's no case for being more efficient. I think efficiency is not the big selling point of the pipe operator. It's more about maintaining code and writing clean code, which is easy to debug, and it says very explicitly what it does step by step. And as it turns out, you can also have this on different lines, just like this. So that is even more cleaner. And I'll show this in examples coming up later. Now,
I think I remember Chris Dushin saying the number of bugs per line are about constant, so you should use wider lines.
fair enough. Yeah. Okay, so now we move on to how to subset rows and columns from a data set. So just some basic functions. Ncol returns the number of columns in a data. So there are 40 columns in our data. And again, to remind you how our data looks like, we can just say data. And this is the data set that we just loaded in. There are a lot of NaN values. There are some issues that will go on. And yeah, ncol gives you the number of columns, and row returns the total number of row. Dim or dim returns the dimension of your data. So there are about 8,700 rows and 40 columns. And call names return column names. So yeah, these are all the columns that we have in our data set. So let's say we wanted to extract all the values in the column num total. So you can use, there are multiple ways to do the same thing. I'll try to cover most of them and then just tell you what I personally use and why. So the first way is to use a single square bracket and provide the column name as a string. So if you do data and then num total, it will return the column num total. If you use $, which is another way of extracting values from a data frame or table, you'll notice that the output it looks different. They are the same, the data is the same, but $, actually returns a vector in R. And when you use this square bracket, that's actually returning a table. Why table, what a table is, that will come later on. I'll just believe it for now. Tables are good, data frames are bad. I'll make the case later on. But yeah, it comes from countless hours of debugging and realizing that R does some stupid things, or no, data frames does some weird things that it should not. Other way to extract a particular column is to use the function called select. So this function is in the dplyr library, which is part of the tidyverse package. So again, let's use pipe operators. That's one of the selling points that I'll just keep coming back to for this bootcamp. Data, which is input, you pass it to select function, let's say you wanted to select num total, the column num total. It's that simple. So data select num total. Unlist, if you actually, we can come back to unlist later, but essentially this is equivalent to saying data $num total. It actually like literally unlists the item inside this data frame or table. And then pull is similar to select and then unlist. So again, there are multiple ways of doing things. I'm just trying to show all the different ways. At the end, I will just share some general tips that I recommend you use. But for now, we can move ahead. So select specific rows. Let's say we wanted to select the first row. So data, if you want to select first row, again, and remember indexing starts at 1 in R, just as MATLAB, compared to other programming languages such as C or Python. So this selects the first row. It gives you all the columns in first row. Now let's say if you want to select the fourth column of first row, then you just say 1, 4. That will give you the item at first row, column 4. Now we still want the first row, but we want first 4 columns. So now we use the colon and then 1 to 4. This is identical in a way to what's SEQ sequence does. So these are like kind of identical ways of doing the same thing. So just to give you another example, we'll use a different way here. This was just a baby example. We are subsetting 1 row. Now we will subset a lot of rows. So I'm just using this R function sample. All it does, it creates n row is like 8700-ish. So sample will return 8700 values with true, false, true, false, true, false. We will select the values which are true and ignore the ones which are false. So I saved it in a variable called Boolean_index. And then we want to select all the rows where we have true. So data, and then first, we want to select all the columns, so we don't provide anything here. We leave it as blank. And now, if you run this, then it will select all the columns. You'll see that the number is approximately half of 8700. That is because sample selects 1 from true and 1 from false. I think it tries its best to be uniform when it performs sampling. And yeah, it selected about 4300 as rows and all the columns. Yeah, this is just another way of saying that now I want to select all the rows, but I want to perform some permutation. So I'll just randomly sample the indices, and maybe these indices are interesting to me and I want to subset them on the data. So if you run this, then you will get the output, but the rows are sampled in a random order. Subsetting columns. Let's say if you wanted to subset, we already saw how to subset 1 column. What if you want to subset multiple columns at once? So again, multiple ways to do it. The most common way is to use square brackets. So C, I think Matt covered this a bit. It just creates a vector kind of. So in this case, it's a vector of characters. So character is just a data type in R. It's kind of string in Python or C. Not exactly the same, but pretty much the same. So we create a vector where each value is the name of the column that you're interested in selecting. I'm saving that in a temporary variable called drop columns. Oh, I think I jumped ahead. Let's come back. So let's say we want to select these 3 columns. So all you need to do is just use data, square brackets, and this. So very nicely, this will return you the 3 columns that you're interested in. Another way of doing this, using the pipe operator, the preferred way, is data, and then you use the pipe operator. It serves as an input to select, and then you are selecting these 3 columns. So this looks natural to me. Data, select these 3 columns. It's simple and elegant. Now, what if you wanted to subset all but these three columns? So you don't want these three columns for some reason. So I think this is one of the solutions that pops up on Stack Overflow. I think this is one of the top solutions because this is a base R solution, if I'm not wrong. So you save it in a temporary variable, and then you use this in operator. So call names of data, remember, it returns all the columns, and then you check which are in the drop calls. So drop calls only has 3, and then you negate that. So this doesn't look good. Like, I would not like this. This is super confusing for me if I'm just coming along from, I don't know. I don't like this. So another way is to use a function called a subset, which allows you to subset columns. So you say data, and then select as an argument, and then you just say minus C, and then provide the columns that you're interested in dropping. So what this says is that first create a vector, and then use minus to sort of negate it. So you discard these 3 columns. And if you run this, you will also get the same sort of output where it will return all columns except the 3. And as you can see, it says 37. We had 40 columns in total. So that's how it works. Best way, or maybe not the best, but a better way is, again, you select, just pass in minus. It's readable. It is explicit in what it does. Data, which is input, use the pipe operator, select. I'm using minus C. So minus C is saying, take all the columns except these columns, or these 3 columns. And there are a lot of functions. Again, I'm not trying to show you or how a function works. I'm just showing you what kind of function exists in tidyverse so that you can Google them when you need it, use it, and hopefully your code will be pretty readable for someone. So just some other functions. What if you wanted to select all columns that starts with num? Well, there's a function called literally starts with. And if you do data select starts with num, it will select all the columns that starts with num, just like that. What if it contains test? So maybe test is not at the beginning, but it contains the word test at some point in its name. So then there's a function called contains, and it selects all the columns that contains the keyword test. You can even do more fancy stuff such as regular expressions. If you want to look more, just Google string R library. This is again a part of the tidyverse package. I would suggest downloading a cheat sheet if you were interested more. Okay, now we move on to select rows that meet certain conditions. So what if you want to select rows such that number of cases are greater than 100, number of deaths is greater than 5 or 10 for some reason. So again, we pass in a condition. So here we are saying data of num total. So data $num total is a vector. Then we say, is it greater than or equal to 1? So we are only interested in cases where it's greater than or equal to 1. We don't care about 0 cases. So this again returns true, false, true, false. We will use this as an index to our data set. So that's what we are doing here. So now this will return all the rows in our data set where num total is greater than or equal to 1. Maybe we are interested in all the rows which belong to the province of Alberta. Then we can, PR name is a column, as you can see here. And we just say PR name is equal to Alberta. And now it will return all the rows where it's Alberta. Better way to do the above thing is again to use the tidyverse function. So the function name is filter. So it literally filters the rows that meet the condition that you pass in. So data input, pipe operator as before, and filter. The condition for filter is that num total should be greater than 1. So it gives you the exact same output. And similarly, province name is Alberta. What if you want to combine these conditions? you want all rows that belong to Alberta, but only when num total was greater than or equal to 1. So you just take the AND. In Python, it's explicit AND or logical AND. In R, it's just a single ampersand. So now your condition becomes this whole sort of thing. And data is input. Filter, you want to filter all the rows where num total is greater than or equal to 1 and province name is equal to Alberta. That will give you all the rows. There are about 578 rows where PR name is Alberta and num total is greater than 0 or greater than or equal to 1. You can also, if you don't like to work with ands or ors in R, you can just use the pipe operator, because remember, pipe operator allows you to sort of decompose function compositions and use it as input-output mappings. So data is input to the first call to filter. This first call filters all the rows where num total is greater than or equal to 1. And then your gain call filter on the rows where num total is greater than or equal to 1. And then this again filters out all the rows where the name is Alberta. We can even do some more compositions. So here, we are not interested in just rows where num total is greater than 1. Maybe we are interested in extremes. So we call here the condition is changed slightly. It says, give me all the rows where num total is greater than the mean of num total. It is that simple. All you need to do is filter, and num total is greater than mean, which is a function in R that calculates the mean of all the rows in column num total. And then you filter again in Alberta. Maybe you like Alberta a lot. So I don't know why I used Alberta, but this is from last year, so we'll see. Our final goal is to create data files or CSV files separated by cases, deaths, hospitalizations based on each province. And hopefully we'll eventually reach that. So combine even more functions. Here I'm selecting everything except num total and num tested, and then filtering out all the rows from Alberta. So data, and then you select, again, because we are using the minus sign, it will drop those columns. And yeah, we have 38 columns and 578 rows. Okay, so pull, this is just like a side comment. Pull is similar to dollar. Pull is useful because you can use pull in pipes, but you cannot necessarily use dollar. So now we move on to dates. So as you can see, date has been read as a character, but technically date has some semantics behind it. You can add dates, you can subtract dates, and R has inbuilt support for this. So you may as well take advantage of it. So I'm defining the format of the date, which is just day, month, and year. And we are using data, filtering cases where it's greater than or equal to 1. And then we are pulling out the date. So we are pulling out all the dates and storing it in variable dates. So now if I print dates, you can see it's dates for every single row. But this is not technically a date. This is still a string or a character. But as I mentioned, we want to perform arithmetic on dates. So in R, there's a data type called date. And if you want to convert a character to date, an integer to date, you can use the inbuilt function as.date. And it takes an argument that what's the format of the input. So the format, we predefined this, which is date, month, and year. And yeah, dates is our variable, which contains character. We're passing it as input to as.date with a particular format. So if I run this, it will look identical. But now it's not string anymore. Now it's date. So you can perform operations such as sorting, adding 2 dates, subtracting 2 dates, and so on. So now I'm using the function sort And this will sort the input by dates. As you can see, this starts from January, March, April. Remember, month is here. So,
What does it mean to add two dates?
so it's a good question.
Like what we
In
get.
most cases, that I have used it is that, let's say you have April 1, 2020, and then April 5, 2020. Then if you do April 1 plus April 5, it will result in April 6.
Okay.
As opposed to a date from 4040.
Yes, exactly. Yeah. And yeah, so the goal that I was like, one of my goals to explain this date process, I wanted to find the day 0. What's the day when we got the first positive case? So that's what we are doing here. So head is an inbuilt function that just takes, that gives you, so this is like entire vector. And because we sorted it, the first element is the day 0. So when you do head, by default, it will print 5 or 10 entries. But if you don't provide anything, but if you say head 1, it will just print the first one. If you do head 10, it will print the first 10. And day 0 after sorting is the first one. So it's 2020 0131. So it's January 31st, 2020. And that is what I'm storing in day 0. So finally, we come to tables. What are tables? Why you should use tables? And I have a hot take on this. I have spent countless, like a lot of hours, maybe because I wasn't an expert at using data frames, but I think you should go with tables, and like it's a recommended data type if you want to do any sort of data cleaning in R. So some very vague reasons to use it. It's an update to the inbuilt data structure called data frame. And some of the key updates that I think are really important is that it does not change column names. So what do I mean by that? Apparently, there are some inbuilt functions which will change the name of columns. For example, if we have a blank space in the column names, because it's a string, having a space is technically allowed, but for some reasons, data frame does not like spaces. So it will replace spaces with underscores without even warning you or something. So if you have that hard-coded in your code, it will break and it will not even give you a warning. It allows duplicate column names. Why would you even do that? I don't know. But you can have 2 columns with identical names. Like it could literally be date and date. You can have 2 columns with date. That doesn't make any sense. But table will just shout at you that no, you have duplicate column names. You need to do something about it. Partial matching of name. This is really bad. This is why I hate it a lot. So what it does is that when you pass, if you have a lot of columns such as date, date _1, date _2, date _3, and if you search for a column date, it will return the first column that matches date. And if there is no column that has date, it will actually return the one which is closest to date, right? So if you have a column, let's say DA, DA1, DA2, and DA3, and you don't have any column with date, but it will return DA because DA matches with date a little bit, and it will not give you any warning. So that like partial matching of names, that's not good. I don't like it. And the only reason is that it won't even warn you that it's returning something. And it also does not allow you to create row names. Row names is something I think pandas prefers people use it. That's more like a personal take, but I personally don't recommend using row names. Just use row indexes. So first row is first row, second row is second row. So if you print data, you'll see that this first column, 1, 2, 3, 4, 5, that's indexed. But data frames allow you to replace this 1, 2, 3, 4 with whatever you want. You can replace that with string, you can replace that with custom index and so on. But then if you index by 1, 2, 3, 4, that doesn't work anymore. You have to use explicitly what you set it to. And that's why I don't like row names. And yeah, in my personal experience, it's quite limited, but yeah, I would just say use tables, don't use data frames unless you like absolutely have to. So just some examples of how to create tables. Again, sequence is the sequence of 1,000 numbers. We'll create a table using the function table. And the way it works is that here, original is the name of the column. So you just pass any number of columns you want in your data set. So first column is original, its value is x. Second column is squared, its value is x squared. Third column is cubed. And again, its value is x cubed. So I'll assign it to x underscore tib. And if you do x underscore tib, you'll notice it's so nicely displayed. And what do I mean by nicely? Well, if I would have used data frame, it would look something like this. It will fill up your entire screen, even though it will not fit. Like you won't barely have like 10 to 15 lines here, but it will print at least 100 values, 100 or 200. I think there's a limit you can set. But if you use a table, it will automatically identify how much space you have. It will nicely print only 10 values, or maybe if I make it a little bit bigger, then it may print more values if I had more. And glimpse is one of the functions, which is, I think it's good, but for some reason it's not used that much. It gives you like a glimpse of the data set. That first column is an int and the values that go on ... I still think just printing data or like x underscore tib in this case, that's like more than enough to see what's going on in your data set.
Why are squared and cubes doubles and not ints?
Squared
like
and
when you square the integers, they
Yes.
automatically become double.
so when you do 0 to 100 or seq, by default it returns an int.
Mhm.
And when you square an integer, it remains an integer in R.
Okay, but like when,
But if you take square root, it will be double.
Oh, but when you
Oh.
did glimpse,
yeah, when you did glimpse, like it says that the
Oh, let me see.
squared and cubed are doubles.
I think that might have to do with the way I squared them. So here I use the caret operator. I might, yeah, my knowledge, or let me think. I know that there is a function. There are some functions which will not change the data type, but maybe I was probably wrong or mistaken. It actually converts int to doubles if you do some arithmetic operations like squaring, maybe summing, or taking mean. So yeah.
yes, I myself am a controversial computer scientist and think every number should just be double because it's easy. Or yeah, it's
Everything
easier
should
that
be
way.
double. Everything should be double. Maybe. So I have worked with some big images in NumPy, and even with R, if you work with big data sets, such as millions of rows, the amount of space it takes between double, integer, and long, it matters a lot because it could be the difference between requiring 16 gigabytes of RAM and 32 gigabytes of RAM if you have, once you reach 1 million items. So yeah.
That adds up.
Yeah, so now we'll just pick some common mistakes in data. And most of this code, like I have just copy pasted this from one of the code base that I worked with 2 years ago. So I don't expect you to understand everything, but it's pretty, like, it's written in a good way. You should be able to follow along if you just go line by line. And yeah. So first we define a few functions. The first function I defined is ABS applied to negatives, which is just applying the function absolute, which just takes the absolute value to all the negative items in the data set. So when we were working with this data set, apparently somehow we had negative cases, negative deaths, or negative tests. We don't know what it means. So we just took absolute in some cases. We just set them to 0 in some cases. again, that was like a domain decision. Someone who knows a lot about this stuff will tell you what to do. In our case, yeah, we zeroed out some small negatives and we take absolute applied to some negatives. So what we're doing here in this function is taking an input data frame and taking a column on which you want to apply negative or apply absolute function. So again, you use the pipe operator. So df, pull the column that you want to use, and then apply ABS. So ABS is an inbuilt function that just takes the absolute value. So if you do ABS of -3, it will return +3. So we are just applying ABS to a particular column and returning the input data frame again. This is again, like you could be explicit, use return df, but you don't have to because R has some functional programming support. So by default, it returns whatever it is there on the last line of function. So in this case, it just returns df, which you modified on the line before that. And we zero out some small negatives. So I'll show you the use case, just like it's literally here, but basically what this function is doing is that there's a threshold that you provide as input. By default, it was -10. This was decided by someone who knows a lot about modeling. So what we are doing here is that anything which is less than 0 in a particular column. So df of col returns a column, and then you're taking all the values which are less than 0, and you take and so that it's greater than threshold. So what this is doing is this is applying negative on all the values between -10 and 0. Because threshold is -10 by default, it could be anything. We store that in an index and just set it to 0. But let's say that if there were a lot of values such that the values were, instead of -7, -8, -9, they were like -100. What does it even mean to have -100 deaths in a day? Like they didn't come back, but something happened, and that's a red flag. We should not allow to go forward. So here we just added a stop, which is a function. It will just stop the execution of code right there, print the appropriate error message, and just stop the execution. So you know that there's something wrong in the data set, you need to talk to someone. And yeah, believe it or not, this happens. This is a very common thing in data sets which are like raw. If you don't clean them, if you just start modeling, turns out that there was an issue with the data and not with your model. So that's why data cleaning is as important, if not more important, than actual modeling.
We want to point our finger at other people.
Yeah, that's the idea, because we got this data from the public government of Canada website. So it's not us who made a mistake, it was them. But again, they're not gonna listen to you. They're like government of Canada, literally. So you have to work with what you have. So we do some data cleaning, and yeah, that's the point. Finally, we just return df. So I'll just run these functions so that they're in memory. Now it comes to fix the outliers. What it means to be outlier, that depends on your particular use case. In this example, what I'm trying to do is zero out small negatives. So if the negatives are small, such as -7, like between 0 to -10, well, it's not like, we will just stay on the conservative side. Again, we were using this for modeling purposes. So we said, okay, if it's -8 deaths, we'll just assume 0 deaths. We'll change -8 to 0. That was a conservative assumption. And number of tests, well, we were again being conservative, so we just changed -7 tests to +7 tests, because doing more testing was a good thing back then. So that was another decision we made. But we didn't really want to count 8 deaths when it said -8, but we did want to count 8 tests when it says -8 tests. So in this function, we are just fixing the outliers. And this is again like a very small example of all the outliers that we encountered. Two or three of them was that in num today, num deaths today, and num tested today, there were some outliers. So we are fixing them. Again, this looks like clean code, which is what you should aim for. There was apparently a special case, and there was exactly one row. We don't know what happened, but when number of cases on a particular day, which was 2209, and it belonged to the province of Quebec, that number was incorrect. And if I'm not wrong, I think we received an email of some sort saying, please change it to 1100 before doing any modeling, which is, I just don't know what to say. That's what we received in an email from PHAC. So like, okay, we'll just make it a hard code assumption. So we just set it to 1100 manually. And we return the input data. So that's our function to fix the outlier. Now we'll try to use these functions on the data that we actually have. So we again read the data. We get no errors, which is good. So this line is just checking if there were any NaN values in num tested today column. So what happened essentially is you do data, you go down. There are two columns. One column is named num tested today. And after a few months, they introduced another column called num tests today. So they had, let's just say, for example, they had values of total testing done in a single day from day 0 to day 100. It was in the column num tested today. And then they just changed the name of the column for some reason. So after starting from day 101, num tested today was blank. And everything was shifted to a new column called num tests today. And we realized this, like it took a while, but we realized that this was an issue with that data set. So what we are doing is just replacing all the NaN values in our original column, num tested today, and just shifting the data from num tests today over to num tested today before we perform any outlier fixing. And again, this is supposed to be a very specific use case for your data set, but I put it in here to emphasize the fact that this kind of stuff is very common when you work with public data sets or any sort of data sets that is not collected or owned by you. So now we just call our outlier fixing function on this data set. And hopefully all the negative values which were there, they're fixed. Just to show some other functions, there is a function in dplyr called count. It returns like a value count of all the columns. So in this case, the column was PR name. So it returned, okay, that's why I don't like sharing the whole screen. Okay. So yeah, PR name was the column, and this is just giving you like a nice summary of value counts. So for British Columbia, you have 592 data points, but for Saskatchewan, you only have 576. So you have to be careful if you make assumption that you have equal number of data points for all provinces. You clearly don't. So this could be like a handy function. I also asked it to sort by saying sort equal to true. You don't have to, but it's sorted by the PR name. So it starts with B, C. Maybe it did not sort, I think. Yeah, I might have to look up what it means to sort here. But yeah. And this is sorting by the province ID. And again, it is giving you the count. So it's saying that province ID 1 has 592 data points. 59 has 592, but 66 has only 576. So how do you join tables together? So we'll just create some baby examples called df1 and df2. And what does it mean to join? Well, let's see. df1 is just this baby table. df2 is this baby table. So as you can see, they share a column called ID. And there's some overlap. Like there are ID 345 is in df1. They're also in df2. So when you join these two together, you want to create a new data frame that contains columns from both the data frames. So there are different types of join. There are left join, right join, inner join, outer join, and full join, and so on. So we'll go, they're like pretty simple intuitively. These are inspired by the SQL database joins. They work the same way. So here we are performing left join. So we are keeping everything in df1 and bringing new stuff from df2. And we are joining by ID. So the column name that we want to perform join on is ID. So you'll see that for 3, 4, and 5, we have B1, B2, and B3 because it was present in df2, but ID1 and ID2 was not present in df2. So therefore, by default, it just replaces it by NA, which is NaN. Another way of doing the same thing is to use the pipe operator. So df1 serves as an input or the first argument to left join, and df2 is the default argument that you are performing join on. And if you run this, you also get the same output. Right join is literally the opposite of left join. So now you're performing join on the df2. So if you remember, df2 has 3, 4, 5, 6, 7 in column ID, and df1 has 1, 2, 3, 4, 5. So it does not have 1 and 2. So when you perform right join, it will say 3, 4, 5, and 6, 7. It's NA because the df1 data frame or table did not have anything for the x1 column. Inner join is like taking an intersection of all the rows in a particular column. So here we are taking intersection by column ID. So this will, oh, I think I skipped ahead. I meant inner join. So inner join is an intersection. It will only return the rows which are present in both the data frames. Full join, also known as outer join, is like a union. So inner join is intersection, full join is a union. So this will return everything and replace whatever does not exist with NA. So these are like some handy functions. You can join multiple data frames together by a single column. And there are also some weird join known as semi-join and anti-join. I have not used them, but they're just there. It will give you all the rows from the first data frame that matches with the rows in second data frame. Anti-join is exactly the opposite of that. So it will give you all the rows in first data frame which do not match with the second data frame, which is 1 and 2.
It's just a keep time. We are 90 minutes in.
Yep. Hopefully 30 minutes should be enough. So yeah, these were like some basic functions we were working with like independently with some small examples. Now we'll just combine this into a final data cleaning pipeline. It's still not cleaning everything that we want to, but it's doing a good job. So we have a lot of provinces in the original data. The idea that again, if you have taken a comp sci course, profs will have repeated this, make it work for something, and then you can generalize it if you define functions in a good way. So here we'll just make it work for one province, and we'll convert it into a function, and then it should work in theory for all provinces. Okay, so just some utility functions. Fix NA. I defined that function to replace all NAs with zeros. Replacing a 0, you could replace it with anything you want. That's more like a domain specific assumptions that you can make. Undo cumulative sum. So this is essentially performing undo cumulative sum. So let's see a very simple example. So when you do sequence 1 to 5, it returns 1, 2, 3, 4, 5. If you want to take a cumulative sum, you can use the inbuilt function cum sum. And then it performs a cumulative sum. So 1 plus 2 is 3. And then 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10 and 15. But what if you want to go the other way around? That's what this function is essentially doing. So it takes a data frame, it takes a column name, and performs undo cumulative sum and returns it. So there's a function in R called diff that does the same thing. So yeah, we'll just define some utility functions, and then there's a function called new and cumulative. What this does is essentially takes a data frame. Time all is like a vector that goes from 0 to final time, which is, let's say, 0 to 600, 0 to 500, and so on. Base column name is the sort of. So let me think. I think. Yes, I remember now.
guys. See you later. Let's see.
Okay, so base column name was just, we'll be using this function to create nice looking data sets for cases, hospitalizations, deaths, and so on. So this is just saying new underscore base column name. So base column name, if base column name is cases, it will just add a new column called new underscore cases, new underscore deaths, and new underscore hospitalization. Again, the idea is to create functions and use the same functions again and again if you are doing repetitive tasks. So we'll come back to this function later on, but essentially the final function that I'm using here, the master function, is to process a province. We'll process the data set province by province. So let's assume again, we are working with Alberta. Just some conversions to convert. The input data set had some rows with all capitalized, all small, some capitalized, some small. Again, the data set is never good. So I just convert it to upper and to lower in case I have to use it. And then to select a single province, we use filter. So we just say PR name equal to province. So now this variable contains a table where all the rows belong to this particular province. And then we are familiar with this code. It is essentially calculating day 0. We saw this above, where we had a whole array. So df pub is a data set. We pull the date. We convert it to the date data type. And we subtract day 0. So this is what I meant by subtracting something. So day 0 in our case was January 31st, 2020. So it will subtract January 1st, 2020 from every single row. So January 1st, 2020 minus January 1st, 2020 is 0.
Okay.
But then February 30 minus January 30 will be, let's say, 30. So it will perform that arithmetic for you, and you don't have to worry about it yourself.
Okay.
I just need to plug in a laptop. So yeah, that's what we're doing it here. So instead of doing it manually, because you converted it to a date data type, it will subtract day 0. So day 0, remember, day 0 refers to the first case, which is this. So just to show you how the subtraction work, let's say if I do, we'll say 2022, and then 12, and then 31. So it will give you the time difference. That the difference was 1065 days. Now you can pass in more parameters or arguments to change the result from days. Maybe you want the difference in weeks. Maybe you want the difference in seconds. You can do that.
Yeah.
So that's like, it makes your job easier. So that's what this is doing. It is subtracting day 0 from each row and converting it to an integer. Because now we want to convert this whole 1065 time difference to an integer. Because at the end of the day, we want to work with a time series data set that starts from 0 and goes on to however many days. So if you do as.integer, it converts. In this case, it did not, because I think there is the order of parentheses.
Mm.
So pipe operator by default take precedence over everything else.
Mhm.
So it first performed day 0, converted it to an integer, and then subtracted it.
Oh, okay.
But yeah, I just added parentheses so that this is performed first.
1972.
Yeah, 1972, that's the birth time of Unix, and I'm on Linux, so that's why I give you that.
Oh,
So, yeah, so finally, once you have the time for, so this is just again subtracting all the rows. I'm taking the maximum. So let's say if the last data point was 1065, I'm just creating a vector from 0 to 1065. So in this case, I'll replace max of something with 1065. So it will return this. This will be one of the columns in our final data set.
Mhm.
Then some details, I won't go into like a lot of details, but yeah, there were some issues in the data set, such as it was a very common thing that a lot of people won't work on the weekends. So what would happen is that you would have an average cases of, let's say, 5,000 cases per day, but because they don't work on the weekends, there will be 0 cases reported on Saturdays and Sunday, but on Monday, you'll have 20,000 cases. But it was actually the total combined tests or cases of Saturday, Sunday, and Monday. So you were just smoothing out the cases and then smoothing out the tests. This was again like a domain decision that was made by contacting people who know how the modeling works or how the test reporting worked. So yeah, there are just some functions. They're defined at the end. So if you are at home and if you want to follow along, you can just run this cell. So they're not like very much related to R, so I just put them at the end. But yeah, you're just smoothing them out. And this is where we are finally using the function new and cumulative. So this was our final goal. The big goal is that we wanted 3 output files: cases, deaths, and tests. In cases, there will be 2 columns: time all, which is just 0, 1, 2, 3, 4, and so on. Then there will be a base column, which was there was a particular format that we wanted, and that for the name of the column was reported incident, confirmed, or suspected cases. And the value will be the smoothed value. And we were also treating the NaN values with this function fixNA. So remember, fixNA is a function, but R allows you to do some functional programming stuff. So that's why you can just assume fixNA is like an object. And this is all being passed to this function new and cumulative. So what new and cumulative does, it takes a particular column. In this case, it is this column containing the cases, and it will extract that column, perform a cumulative sum, and just return a sort of data frame or a table where it will have 3 rows. And I will show you the output later on. We do the same thing with deaths. The column name is different. We do the same thing with testing. And again, the column name is different. And finally, we return it. We return a list of tests, cases, and deaths. So this was like our big, not really the biggest goal, but one of the goals that the data cleaning pipeline was doing back then. So we run this. And finally, we are there. We did a lot of work. We made it work for one province. We made it work for one particular output file testing. And then we made it for cases and deaths and so on. Now all you need to do, just run a for loop over all the provinces. So again, if you remember, if you do data of PR name, which is the name of column, it will contain duplicates because we have like 8,700 entries. So we take unique values. Unique is an inbuilt function in R that will give you the unique values. And then you just iterate it for each province in this. Print the province, convert the long to short. So if it's Alberta, it will convert Alberta to AB. That was a hard-coded convention that we were using. As.date. So this was our day 0 that we hard-coded again by checking what is going on in the data set. Different data sets have had different day 0s. And then you have, finally, you call the function process province. So this takes in a few arguments. It takes in the province, it takes in the data sets, and it also takes the short form of that province, then day 0. Then what's the format of the date? This is required by the R inbuilt function so that it can identify, because there is no restriction that date have to look like 2020-01- something else. You can also use backslash, you can use forward slash, you can use anything you want. Maybe you don't want the 2000, you just want 20, 19, 18, 17. You can specify that by changing this format of the date. And then we are just writing it out to files. So read CSV, reads CSV files, write CSV, writes the output. So again, this is different from write.csv. I prefer to use write_CSV because this is still part of that tidyverse ecosystem. So the first argument is what you want to write. So in this case, we want to write the testing table. Remember that this returns a list. And there are 3 items in the list. Table 1, testing, table 2, cases, and table 3, deaths. So here I'm writing tests, and then cases, and then deaths. And then it's just the path of the output file. So it's output file, output path that is determined. I've hard coded it here for now. And then it's just saying testing_pt. So if it's Alberta, its short form will be AB. So the output file will look like testing_ab.csv. And once you run this, and let's go to the folder, output. We go there, that's where we have all the files. So this was our final goal, to separate out take the input data set, perform cleaning, and get output data files in a particular format that we wanted to give an idea of what it looks like. Let's say cases sk.csv. So that's how it looks like. Just 3 columns, nice and clean, no negative values, no NaN values. It goes from time 0 all the way down to whatever the final date is. So in this case, it's 615. New cases, second column is the new cases in a day. Third column is the cumulative cases that we have seen so far. And yeah, this was so this CSV file was input to the modeling that we were performing. So this will be input. This could be input to something like what Matt showed if you're doing some regression, or if you're doing some classification or some other sort of modeling. And yeah, and by the way, this is a command line tool called Data. It is really good, and it has some really nice features. You don't need Excel to open CSV file, and it is really, really fast. It could open up CSV files with like 10 million entries in an instant. And yeah, it has some nice features. I don't know all of them, but if you want a summary, you can press Shift-C and it will give you a summary. If you press enter again, it will give you a histogram count automatically. And maybe this doesn't look that good, but it could also do command line graph plotting. So just to show you a demo, sort of, it does a command line graph plotting.
Oh, that looks a lot nicer than you give it credit for. Yeah.
And we can also do multiple columns. And let's say if you wanted to actually browse through. So this is actually in cursor. If you go and press enter, it will open up all the data points that were in that small cluster. So like this is like a really good command line utility you could try and take a look. And yeah, so that was like our big goal, that we had this data set that had a lot of things. We were not interested in all the columns, but we were interested in particular columns. We had to perform data cleaning and then make some assumptions such as absolute values, negative values, and so on. So the point I was trying to make here is like not showing you what each function does. I was trying to show what you could do if you know some functions. And if you don't know, you can again very easily get cheat sheets and Google things up. But this is like a very good way. This could scale up to really big data sets. and you can convert this code to a script, and then you can just keep running it on an automatic basis. And yeah, I do have a small section on parallel computing in R. It's kind of like a digression from what we were doing so far, but I think this was part of last year's R Bootcamp. I was just trying to show the capabilities of R, and if you wanted to do some parallel computing. So before you even start with parallel computing, I copy pasted this quote from Donald. I'm not trying to pronounce his last name, not Knuth, I don't know. It's weird. But yeah, he said he had a like a very famous quote that forget about small efficiencies. About 97% of the time, premature optimization is the root of all evil. Yet we should not pass up opportunities in the critical 3%, and a good programmer will have such like sense of reasoning, and it will be wise with the critical code, but only after you know that 3% of the code. So yeah, R has some function that allows you to do some parallel computing with minimal effort. So there's a function called do parallel, which automates a lot of like underlying things that you need to set up before doing parallel computing. So where would you use parallel computing? So a very famous, arguably, like it's kind of not really that old, but random forest is a machine learning algorithm that could take a long time depending on your data set. So let's say that you wanted to train 100 models, and if you try to do it one by one using a for loop, it will train one model on a single core, then train second, third, fourth, fifth, and so on. But if you wanted to train that in parallel, you could use this library and do it. So I'll just demonstrate it on like a very simple baby example. So for those of you who are not from stats background, IRIS is a friendly data set. Like if you're majoring in stats, or if you've taken any machine learning course, this is like a very common data set that you would have worked with. And hey, again, this printed a lot of stuff because IRIS is a data frame and not a table. Everything would have been nice if it was a table. So if you do as dot table, there it is. Now it's nice. So yeah, it has some columns. Flower, I think it's a flower data set with length, width of petals and sepals of different species of flowers. And our goal is to try and predict the species. So yeah, I'm just setting up some temporary variables. Number of observations is the number of rows. Trials, I'm just trying to indicate that I want to train 1,000 random forest models. If you do it one by one, it might take a long time. But if you want to do it in parallel, it could be fast. So the serial version is nothing too special for I in number of trials. I'm just sampling with replacement just to make sure that we don't get the same model again and again. So we shuffle the data set. We call the random forest function. We are trying to predict species, input data, importance, proximity. These are like the machine learning parameters that random forest have. It has a lot more you can tweak around, but I'm just trying to show what you could do. So finally, we are interested in the coefficients that we get after training this model. So if you're doing a simple linear regression, coefficients will be something like the coefficients of the trained model. So beta 0, beta 1, and so on. So we'll just try and time it. Let's see how long it takes. I might have to change it down from 1,000 to 100. We'll see. But yeah, in the meantime, how do you get started with parallel computing? So the first step is to move from regular for loops to parallel for loops. But before we go there, there's something known as for each. So this is very similar to the for each in Java, where you can iterate without an actual index. So yeah, it looks like it just finished. It took about 28-ish seconds to train 1,000 random forest models. And this is the same thing, but it's just a different syntax of for loop. So instead of saying for I in 1 to trials, this is just saying for 1 to trials, just do this thing. So this should, in theory, take the same amount of time. This is just a different way of writing for loops in R. So yeah, we'll let it complete. But here's the main sort of crux of doing parallel computing. So there are two functions that you could use. Again, okay, it looks like it finished. It took about 28 seconds in both function calls. You call make cluster. So make cluster creates a local cluster of cores that it is allowed to use to train models in parallel. So detect cores is again an inbuilt function that detects the number of cores. So on my laptop, I have 12. If you have access to some big server, it might have 48, 64, 128 cores. So I'll be using all the cores. You make a function, make a cluster, and I'm saving it to a temporary variable CL. Forget about fork. It's some technical detail. I will not get into it. If you want to know more, feel free to contact me, or you can even just Google it. If you are from a computer science background, you should be able to follow it. And then we register the cluster that we created. So this is again the inbuilt function in library do parallel, and this takes care of a lot of like small details that you would have to do manually to do parallel computing in R. But all you need to do is just these two lines, and then you move from for each to do par. So in the previous for function, I just had do. So this was the serial version of for loop. You just replace do with do par, and this performs parallel model training. So now if I run this, and one of the reasons I shared my screen, you can see the CPU usage on this corner. It's like 82%, and it's high, and it's done. So it took about 4.7 seconds. Originally, it took 28 seconds. So yeah, that's just like a little thing. It's not necessary that it will always scale. There are a lot of like small details, but just sort of an idea that if you're doing some model training, if you have like 100,000 linear regression models to train, because you are looking for some randomness in the data, then training them one by one will take a long time. You can use something like this to train them in parallel and be done fast. Yeah, just some final tips for performance computing in R. It could be parallel computing is really useful if done properly. In our case, we just perform model training on each iteration, and training from one iteration was totally independent from other ones. So we didn't have to do any extra work. But if the result was dependent on previous iteration, then you can obviously not do parallel computing. Some other tips is, do you prefer to use inbuilt vectorized function instead of actually or explicitly using for loops? Such as if you want to calculate the sum of an array, don't do for I equal to 1 to the n and just looping over every value and then summing it. Just use the inbuilt function sum, because that is written in C, it is compiled, and it's built for vectorized operations. And another like sort of tip that I would like to give you, if you want to do some performance computing, is that write a small function or small snippet of code that works for either one column or one row in the input data set. And just that's all that function does, nothing else. And then you can use this function called map in the library per. And this is also part of that tidyverse package, and it has kind of like a cute name per. I think it has some hat emoji or something like that. Yeah, it's per, and the function name is map. So what this will do is you provide two arguments. One is the data set, and second is the function name. So it will perform that function on each item. It could be each row or each column of the data set. And that could speed things up, and it's also less error prone. Instead of doing explicit for I in this, for J in this, and so on. And if nothing else works, you could consider rewrite your code in C or C++, and then you can call that compiled C or C++ code from R. You can get significant speed up, like I'm talking 1,000 to million times, depending on what you are doing. There's a learning curve to do it correctly, and just make sure you're not reinventing the wheel. It's possible someone has already done it or a function exists. And yeah, again, Hadley Wickham, I like this guy, like he's the main author of Tidyverse. I think it was one of his PhD projects or something. He wrote the entire Tidyverse. I think most of the original version of Tidyverse were written by him. If you have ever heard of ggplot, that's also written by him partly. So yeah, if you want to use R for data processing stuff, only use it if you are going to use Tidyverse and nothing else. And yeah, I think that was it. Just some extra code. And again, you should be able to run this on your local computer if you follow along with the data set I provided.
Yeah.
Yeah.
Well, thank you very much, Guillaume. I'll give you one applause for a speaker.
Yeah.
And thank you very much, Don and Darian, for showing up here. That means a lot to us.
Yeah.
Anyways, I will